All right, the exponential model 199.1 times e to the power of 0.028 t describes the population of a country in millions 2 years after 2003. Use the model to determine the population of the country in 2003. So let me write down the model. A equals 199.1 e to the 0.028 t. Okay, and so t is years since 2003. So in 2003, t equals 0. Okay, so a equals 199.1 e to the 0.028 times 0. This is just e to the 0, which is 1. So it'd be 199.1 times 1. So it'd be 199.1. So it's just going to be whatever that initial value is. Okay, which is 100. Whenever you have an exponential, you put that first. So 199.1. A little slow this morning. Come on. Maybe. There we go. All right, next question. The exponential model a equals 673.4 e to the 0.013t describes the population of a country millions t years after 2003. Use a model and the population will reach 709 million. Okay, so 709 will be a 3.4 e to 0.013t. So the first thing I'm going to do is I'm going to divide by 673.4 after I plug in 709 for a, because that's the new amount. So 709 divided by 673.4, 1.053. And I got to be careful about the rounding on this because it might get me on some of these word problems. Okay, it did on the last section. Now I'm going to take the ln of both sides. I'm going to do the exact in the calculator. So what I'm going to do, I'm going to do ln. And I'm going to grab this thing up here. Well, it's kind of exact because it's, I don't know if it's really exact, but close enough. So I got 0.052. So 0.052. Sorry. 0.052 is equal to 0.013t. Now we divide by 0.013. 0.013. So this divided by 0.013. T is equal to 3.96. So what you're going to do is you're going to do 2003 plus, which would be around 4, plus 4, so it'd be around 2007. So 2007 would be the year. Hopefully, it's the year. Slow this morning. We're having some. I think the Math Excel is having some technical issues. It was loading slow. So 3A, the population of the country was approximately 6.11 million at the 2040, and it's projected to grow 9 million to 9 million. Use the exponential growth model, or T's number of years after 2000, A naught's number of millions. Find the exponential growth that models the data. Okay, so A equals A naught e to the kt. Okay, and so it starts off in 2000. It was 6.11 million, so that's going to be A naught. Okay, in 2040, it grows to 9 million, so that's going to be A. And then T is going to be 2040 minus 2000, so it's going to be 40. And I'm going to solve for K. Okay, you can move this so you could see this better. So so 9 equals 6.11 e to the k times 40. So we'll divide by 6.11. So 9 Let me move this over. 9 divided by 6.11. Let me see if I can. So the other day I did this on this, and it was the brightness was not working with the camera, but now it's wanting to work a little bit better today. So we're going to keep it e to the 40k. Now we'll take the ln of both sides. So ln of 1.473 equals 40k ln of e. That cancels. So I'll just divide by 40, divide by 40. So I'm going to take the ln of this answer and divide it by 40. And now how many, they want 2 decimal places, so 0.01. Okay, so k will be 0.01. So my model is going to be a equals your initial amount, which is 6.11, e to the 0.01 times t. So that should be my model there. So 6.11 e to the power of 0.01 times t. Okay. Now for B, the country would be 14 million in the year. So when will it be 14 million? 14 equals A. So 14 equals 6.11 e to the 0.01 t. I'm going to divide by 6.11, divide by 6.11, and then 14 divided by 6.11, 2.29 equals e to the 0.01 t. Now I take the ln of both sides. So ln of 2.29 is equal to 0.01 t ln of e. That cancels, so I'll divide by 0.01, divide by 0.01, ln of, and I'm going to use the exact here, or somewhat exact, divided by 0.01. And so t is going to equal 82.91 years. Now you're going to add that to your 2000. So 2000, and we're going the nearest year, right? So 2000 plus, and I'm going to add 83. So it'd be 2083. So 2083. All right. Next question, number 4. The half-life of a radioactive element is 5 seconds. So the half-life, taking some notes here, is 5 seconds. If 80 grams are initially present, so 80 grams initial, taking some notes here, how many grams are present after 5 seconds? Okay, so after 5 seconds. So present, you don't have to do any complicated math. Is this all there is to this? Okay, it's five-part question, 10 seconds, 15 seconds, 20 seconds, okay. So 5 seconds, okay. So after 5 seconds, the half-life's 5 seconds. All you got to do is take 80, so 5 seconds. You just got to take 80 and divide it by 2, because in 5 seconds, half of it's gone. So it'd be 40 grams. So it'd be 40. You actually don't have to set up equations on this one. You can, but it's not worth it. Now, 15, so every 5 seconds you're losing. So for 10 seconds, you see every 5 seconds you're losing half of it. So like half of more of it's gone. So 40 divided by 2 would be 20. So 20 grams. And then after 15 seconds, just not worth it to set up the equation here. You're losing half more, so it'd be 10 grams. Okay. And then after 20 seconds, you take 10 divided by 2, it'd be 5 grams. I don't know if I need to draw an arrow there to that one, to that one, to that one, so it'd be 5 grams. And then 25 seconds, around 1 decimal place. So 25 seconds, It'll be 5 grams divided by 2, it'll be 2.5 grams. I shouldn't be doing the grams part, but so all you have to do is just keep on having it there. Kind of gives you a little application of the, we're not really doing much rigorous math, but it kind of gets you to see the half-life, how it works there in a problem. So example 5, or question 5, prehistoric cave kings were discovered in France. The paint contained 35% of the original carbon-14. Use the exponential decay function to estimate the average, to estimate the age of the percentage of paint, or the painting. Okay, so 35% of the original. So what that means is 0.35, so times A naught is equal to A, because it has 35% of the original, so 0.35 A naught equals A naught E to the negative 0.030. So I gotta be careful here. 1, 2, T. You could basically just cancel the A naught. So I can divide by A naught, divide by A naught, cancel, cancel. 0.35 equals E, the negative 0.00012 T. Take the ln of both sides, so ln 0.35 is equal to negative 0.00012 T ln E. That cancels. Okay, I'm making sure I have enough zeros here. To negative 0.00012. So ln of 0.35 divided by negative 0.00012. So T is equal to 8,748.5. So it would be, I'm a little careful about the rounding here because it messed me up on the last time. I'm gonna say 8749. All right, let's try 8748. This is where this gets frustrating. Okay, whoops. Okay, 35% of the original painting. Okay, model to 21. I forgot to put the 2-1 here. I apologize. I'm glad you could see me mess up, but that's going to make a difference here. 8,676. So 8,676. And that does matter, even though it's a way out there. Okay, I apologize about that. So 8,676.2. I told myself I had to be careful, and then guess who didn't follow their own advice? That was me. That's what you get. So number 6. So maybe you'll do better than I did. Complete the table shown on the right, the half-life of a certain radioactive substance. So the half-life, so we've got the decay rate is K is equal to negative 0.091. And so I want to know the half-life. So in half-life, I want to know when A is 1/2 of A naught, or 0.5 of A naught. So 1/2 of A naught is equal to A naught times E to the negative 0.091 times T. Okay, so you put K in that spot. Basically, these are going to cancel. Okay, because you can divide both sides by those. I'm going to take the ln of 1/2 and then negative 0.091 ln of E. That cancels. Oh, T. Once again, being careless there. Divided by negative 0.091, negative 0.091. Okay, so ln of 1/2 divided by negative 0.091. So T is equal to 7.617. How do they want this to go decimal places? So 7.6, let me make sure 7.6 works. We're writing it down. Okay. Okay, let me write that down there. 7, with the table below, I've given a half-life. I got to find the decay rate. Okay, these are good questions. So the half-life is equal to 2022 years, and that's equal to T. Okay, so then, and for half-life, I should have put, I'm sorry, well, it's fine, but with half-life also, 1/2 A naught is equal to A. Okay, so 1/2 A naught is equal to A times E to the K times 2,222. Okay, and so that cancels. So I'm going to do the ln of both sides. So ln of 1/2 is equal to 2,222 K ln E. That cancels. So divide by 2,222. So ln 1/2 divided by, and this is going to be 4 decimal places, so negative 0.123 zeros, and then 312, 6 decimal places. Nice. Okay, that's good. So perfect. 0.0, because you have to go more decimal places on this if you want to do it right whenever you're using it. Because if you don't, then it'll make your answer more. It'll make your answer off more. Okay. Use exponential decay. We'll have to move this up here. So number 8, the exponential decay, the half-life of certain subjects is 19 years. So the half-life, is 19 years. How long will it take a sample to do 92% original? So 92%, that means that 0.92 A naught is equal to A. So first off, I've got to solve this for K, and so half-life 1/2 A naught is equal to A. So 1/2 A naught is equal to A naught E to the K times 19. A naughts cancel. So then I'm going to take the ln of both sides. And then 19K ln E, that cancels. Divide by 19. Divide by 19. So K. So ln of 1/2 divided by 19 is negative 0.0365. I'm not sure how many. 4 decimal places. Okay, 4 decimal places. All right, and that's important. They got to tell you, because if they don't tell you, then that's going to make an impact. So now we're going to do 0.92 A naught. It's equal to A naught E to the negative 0.0365 times T. Okay. Those cancel, and I'm going to do the ln of 0.92 equals negative 0.0365 T E divided by negative 0.0365, negative 0.0365, so ln 0.92 divided by negative 0.0365, and so T equals 2.28 years. And they want to do the 1 decimal places, so 2.3 years. It'll take 2.3 of these years, okay, years for the sample to the, so 2.3 years. I'm not going to write out all that. Okay, I'm a little worried. We're trying to conserve some space here. All right, 9, the logistic form function describes the, let me write this down, f of t equals 102,000 divided by 1 plus 5,900 e to the negative t. Number of people that became ill with a certain influence after T weeks after the initial outbreak. How many people became ill with the flu when the epidemic began? So when the epidemic began, so A, when it began, t equals 0. And so in this case, it would be f of t is equal to 102,000 divided by 1 plus 5,900 e to the negative 0. So that's just going to be 1. So it'd be 102,000 divided by 5,901. So 102,000 divided by 5,901 is 17.28. Do we want to go to 17? So 17.29. So initial 17. And then on the number after 4 weeks, so 4 weeks, that means t equals 4. So f of 4 is equal to 102,000 1 plus 5,900 e to the negative, or e to the negative 4. I'm going to use alpha trace here. Alpha trace and do this. You just got to be careful with this. This one's got a lot of. Just want to be careful. Everything you and your calculator are on the same page here, because it kind of is a little bit complicated. And so f of 4 is 935.25. So 935. Okay, and then after, what was the limiting size of the population? So the limiting size of the population. The limiting size is just the numerator, so it should be 102,000. Let me write that down. All right, logistic growth model is world populations given is here. According to this model, when the world population be 8 billion. So let's look at this. We've got, looks like we got a solving one here. So we've got f of x equals 12.57 divided by 1 plus 4.11 e to the negative 0.026x. So I want to know when 8 billion, that's when f of x equals 8. Okay. I'm going to solve this. So 8 equals 12.57 times 1 plus 4.11 e to the negative 0.026x. We're going to multiply both sides by 1 plus 4.11 e to the negative 0.026x. So I'm going to write this down here. Actually, I'm going to use this extra room I have. So 8 times 1 plus 4.11 e to negative 0.26x is equal to 12.57. And then I could divide by 8, actually. I'm going to divide by 8. I don't know if that's the best way to do this. But, so 1 plus 4.11 e to negative 0.026x is equal to 12.57 divided by 8. 1.57. And then I'm going to subtract 1. So 4.11 e to the negative 0.026x. This is so unorganized. 0.57 divided by 4.11 divided by 4.11. Let me draw an arrow here. It's going back and forth. So e to the negative 0.026x is equal to divided by 4.11. Sorry, you can't see my calculator. Let me move this over. So divided by 4.11, it's going to be 0.139. Now I'm going to take the ln of both sides. So negative 0.026 ln e equals ln of 0.139. That cancels, so I'm going to divide by negative 0.026. So x is here. So it'll be x is equal to ln of this divided by negative 0.026. 75.898. And so that would be around 76 years. So I'm going to add that to here. So 76. So 1965 plus 76. 1965 plus 76 would be 2041. I hope this is right. Okay. Let's try 11. The logistic growth function is get miles a percentage. I'm going to write this down. The P of X is equal to 90 divided by 1 plus 271 e to the negative 0.122x. Percentage of Americans who have some coronary heart disease use a function protect 58-year-olds who have some. So P of X Americans who are X years old. So 58. So this is going to be 58 for X. So X equals 58. So this is a pretty simple one. So P of 58 is equal to 90 divided by 1 plus 271 e to the negative 0.122 times 58. I'm going to use that math. I'm going to use the alpha trace to get that fraction. So 90 divided by 1 plus 271 second ln negative 0.122 to the power to 58. So 73.23. So that would be, what percentage would have that one decimal place? So 73.2. 73.2%. So 73.2%. All right, trying to fit all this on one paper. There is a chance. I say that, and then we got a part 3 question, so maybe not. A bottle of seltzer initially at a temperature of 83 degrees, so initial 83 degrees. Is left to cool in the refrigerator at 37, so cool to 37 degrees. After 10 minutes, the temperature is 58, so 10 minutes, 58 degrees. Complete parts A through C. So A used Newton's law of cooling. I better write down this formula. T equals C, and then plus T naught minus C e to the KT to find the temperature after T minutes. Okay. So first off, I got to find the constant. And so I know I'm wanting the temperature that I'm wanting it to get to, or that currently I have it's at 58 degrees, and the initial amount is 83. So 83 degrees plus, and then I'm sorry, I had this backwards here. The room itself, the refrigerator is 37, so 37 is your C, sorry. And then your initial amount is 83 minus 37, e to the K, and then that's after 10 minutes. So, okay. So we'll do this, we'll subtract 37, so 58 minus 37 is 21. 83 minus 37 is 46. E to the 10K divided by 46, so 21 divided by 46 is 0.4565, and that's e to the 10K. Now we'll take the ln of both sides, so ln of 0.4565, 0.4565. 5 equals 10K ln E, divide by 10, I'll write this over here. K is going to be ln of this divided by 10. So it would be negative 0.078. How many decimal places they want? Oh, 4, so 84. So T will equal the initial amount, or the amount that's in that environment it's in, 37 plus, and this is going to be 83 minus 37, which would be 46. Yeah, 46 e to the negative 0.0784 t. So there's your first part. Feeling this is going to take more room. So 37 plus 46 e to the negative 0.0784 t. All right, so now to part B. What's the temperature after 15 minutes? So B, 15 minutes. So that's T equals 15. So T equals 37 plus 46 e to the negative 0.0784 times 15. I'll be able to put this one over here. We can get this one done quickly. So 37 plus 46, second ln, negative 0.0784 times 15. So 51.19. So after 15 degrees, nearest degree, so 51 degrees. So 51 degrees. When will the temp reach 50 degrees? So when will it reach 50 degrees? So when will the T equal 50? So 50 equals 37 plus 46 e to negative 0.0784 t. So subtract 37, subtract 37. So I've got 13 equals 46 e to the negative 0.0784 t. Divided by 46, divided by 46. So 13 divided by 46 is 0.2826, and that's e to the negative 0.0784 t. So you do ln of 0.2826 is equal to negative 0.0784 t divided by negative 0.0784. So ln of that divided by negative 0.0784. So 16.12, so the nearest minute. So t equals 16.12, so it'd be 16 minutes. All right, so let's look at this one, 13. I'm going to sketch out this table here. So this is not good video. I probably should have waited, should have paused here. But we're going to plot this on a scatter plot and see what the solution is. And then we're going to analyze it to see which type of regression would be best. Okay, so we're going to look at some different regression models. Okay, and so they call this curve fitting. That's what this is called. So it looks like they start at 0, 0. So we're going to start at 0, 0 here. Okay, so we'll go 0, 0. My x's go to, let's go to 50, 50. So 0 to 50. So 10, 20, 30, 40, 50, and then 10, 20, 30, 40, 50. Okay. So 22 and 8%, 29 and 9%. 33 and 15%, 36 and 20%, 42 and 37%, so that goes a little higher, and then 47 and 51%, so I probably need to go to 60 here. Okay, so there's my scatter plot. Do I see anything matching that? Oh, looks like this one. Oh, look at exponential to me. It's exponential. Exponential is one of the options, so it does have a little bit of an exponential feel to it. Well, to formally prove this, though, what I need to do is I need to go to stat, enter. I'm going to go here, and now it's not showing up as well. Sorry about that. Had some problems getting this clear down, I'm gonna enter these in here. I'm thinking it's gonna be exponential. I'm pretty confident, but you never know. Regression, doing the R values and looking at those, but it definitely looks exponential to me, but it's probably gonna have a high value, R value with the linear one as well. Okay, and we talk about this in my statistics classes. We've talked about how sometimes they could look like an exponential, but have a strong linear. So I'm gonna go to stat calc. Actually, before I do that, let's go to mode stat diagnostics. I want those to be on. So then stat calc linreg. So let's look at the linear one, L1, L2, and the linear one. See, that's pretty strong. So linreg linear had an R equal to 0.943. Okay, so now let's go to exponential. So we're going to EXP reg. L1, L2. EXP reg, yeah. See, I was thinking, and this is kind of what I expected. R equals 0.978. I expected the R for that one to be higher because it looks like an exponential curve. So that's what I was guessing, but you never know with this. And so now next we're going to look at logarithmics. Let's do ln reg 0.895. So log 0.895. So exponential's the winner here because it has the highest R value. You can't even see that. Exponential has so exponential function. Okay, we're gonna have to go to a new sheet of paper. Dream of fitting it on one did not pan out today. Okay, so let's go to 14. On 14, we have the data of intensity. I'm just going to kind of sketch here in loudness level. I'm just going to put loudness. So I've got 0.6, 5, 19, 96, and then 110, 119, 129, and then 144. Okay, and they're going to start at 100 when they do theirs. They're going to start at 100. You could start with X. You have to start at 0. They'll go 0 to 100 here. And so 100 to 150. So 110, 120, 130, 140, 150. And then we'll go 0 to 100, 20, 40, 60, 80, 100. So 110 and 0.6. I'm sorry, 0.6. Oh, goodness, I did this backwards. I'm sorry. This is 0. X is 0 to 100. Y is 100. 110, 120, 130, 140, 150. Jeez, get it together. So 0.6 and 110, 5 and 119, 19 and 129. So it goes about right there. And then 96 and 144. This is kind of looking a little maybe logarithmic here. Okay, so I'm guessing it's going to be, you had 19 and 129. Looks like D. Okay. This is not plotted very well. I apologize. Kind of doesn't fit the logarithm. This looks logarithmic to me. If you think of all the graphs we've covered in here, so I'm guessing a logarithmic function is going to be the winner here. So I'm going to go to stat, enter, go to the top, press. I'm going to do it on there here so you could see it. Press clear, press down, select the list, clear down. 0.6, 5, 19, 96, and then 110, 119, 129, 144, stat, calc, ln reg, so log, and I'm going out of order. I mean, it doesn't matter what order you're in. I've kind of have a feeling it's going to be the logarithmic one. And R is 0.982. Let's do linear. So linreg. R is 0.924. Pretty strong. Let's go to expreg. R is 0.908. So exactly what we thought. .908. So we want to use the logarithmic. I spelled that wrong. I always spell logarithmic wrong. Logarithmic one wins that one. The highest R value. Okay. Let's go to 15. So logarithmic there. 15, replace in terms of base E. I'm going to write this over here. This is not that bad. So in terms of base E, so we've got y equals 96, 3.4 to the power of x. Okay. So what you're going to do is you're going to keep this the same, the 96 the same, and then you're going to do e to the ln of 3.4 x. Okay? So then you're going to take the ln of 3.4, so 96 e ln of 3.4 is 1.22. How many decimal places do we want? Oh, natural logarithm. So we're going to leave this alone. Okay. How about I read the directions? I apologize. So we're just going to leave this alone because we just want the natural logarithm in there. So 96 e, and then I did shift 6, ln of 3.4 x. Okay. Now, simplify the answer. So simplify this. Okay, so we're just going to type this in there. So y equals 96e to the 1 point, how many decimal places? 3 decimal places, 224x. So y equals 96 e 1.224 x. Okay. Last one, rewrite this in terms of logarithms, and so it's a two-part. So you got y equals 2.1 to the 0.3x. So I'm going to do y equals 2.1 e to the ln of 0.3x. So we're going to do it as terms of the natural logarithm. So 2.1 e shift ln of 0.3, and then I think I need to parentheses on the 0.3 times x. Then we're going to simplify. So then that will simplify. Y equals 2.1 e. So ln of 0.3 is negative 1.204 x. Okay. 2y equals 2.1 e shift negative 1.204 x. Whoops. Did I do something wrong? ln of 0.3, so 2.1 e to the ln of 0.3, 04. Oh, they already have y there. I'm sorry, they already have y there. Well, I should pay attention. There you go.